you to think what we're about to do is going to screw you up for Wednesday, because I guarantee you it's not. All we're going to do, what I'm talking about right now, for the next hour-ish. Yes, we're going to begin. Don't even write the word binomial in your book yet, though. Because I don't want you to even draw the connection between the fact that we're doing anything different. Because honestly, we're not. We're not doing anything different right now. What we're doing right now, or what we're about to do right now, is to paint a picture of what's called the binomial distribution. Now, the binomial distribution, it ends in the word distribution, which so does the word probability distribution. Let me just show you.
Mind blown.
Well, this might blow your mind, Teddy. This might blow your mind. Hang on a second, hang on a second.
What are you going to do?
Hang on. Hang on, there's a beautiful, I gotta find it. Is this it? No, we can use with this, is fine. So, I don't know if you can see these, all these right here. Boom, 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 boom. All of these are different kinds of distributions. Okay, there are a butt ton of them. In 243, I brought it down to simply two that I want to focus on. The binomial and the normal. The binomial and the normal. In 244, we'll pick up a couple more. The t, the chi-square, the f. There are literally hundreds more, maybe even more that I'm not aware of. This is Wikipedia, I'm not sure. Here's your chi-square, that's one of those we do in 243. So what I want to focus on right now is one subset of the larger idea of a distribution probability, which is the binomial. But don't even write down the word binomial right now. When you hear the word binomial, what do you think of? Two. Good. Think about why it's called this as we go through today. And I want to start by introducing this. I discovered this about 2 years ago. This is the best way I've decided to introduce this. By you guys meeting my chicken flock. Because this seems to be the best way. Ooh, let me back up there. This seems to be the best way, at least it seems, as far as student success goes, as I track the understanding of this, this seems to generate the most success. I don't know if it's because it's fun to talk about chickens. I don't know if it gives you a nice visual. I have no idea why, but for whatever reason, this is the best way compared to a traditional way. So Nancy, Mary, Bertha, Marge. They were named the day we bought them. And the day we bought them, they were 1 day old. Okay? Anybody have chickens in here? Anybody have chickens in town? A couple have chickens. Okay, good. So did you guys buy them from public? From babies? We get it. Good. Now, when you go in and buy them, here's what happens. We go into the store. I sent Max in. Max, go get 4 chickens by Bend like code. You can have up to 4 chickens on I think it's a third of an acre, or a city lot, basically. City lot, you can have up to 4 chickens by code. Any more than that, it breaks code. I won't tell if anybody's got more. But I only have 4, there they are right there. Now, we named them when they were a day old. But here's the deal. When I walked in, if you've ever been into the feed stores around early April, I think April 1st, April 2nd is when they bring the day old chicks in. They put them in these bins, and there's like hundreds of chicks running around in the stores, like literally hundreds of chicks. And they're sorted out by species. You know, you got the Americanas and the Delawares and the Orpingtons and the Barred Rocks and the Sex Links, and Pullets is the female chick. And I'm looking at these things in these bins, and they're a day old. And Max grabs one and hands it to me, and I'm holding this thing, and it's adorable. It's a marshmallow peep. And I go to the guy, I say, how can you tell this is a girl? And he's like, oh, we don't know if for a fact it's a girl. I'm like, oh, that's great. Because we want girls. We want eggs. That's why we want chickens. We don't want to raise them to raise more chickens. I don't want a rooster. I want girls for eggs. So he's like, well, we've got the sexing process that's 90% accurate. So basically, what I'm looking at is I'm looking at a bin full of baby girls. And it's 90% girls, is what this guy's telling me. So there's a bin with a bunch of pullets in that are called pullets. 90% of them are actually girls. The other 10% are roosters that got mislabeled. False positives, if you will. We'll get more of that in this class, too. Does that make sense? So I go, Max, here's a box. They give you a little Happy Meal box, a little tiny cardboard box. And you put the chicks in the box, and you get it home, there's poop everywhere. It's amazing. And $5 later, there's 4 birds in your house, and they're pooping on everything, including you. So here's the question I have for you. Hundreds, if not thousands, of birds in the store. And Max goes in there and pulls 4 of them out. Is this independent or dependent sampling? What do you think? Let's hear some votes. I hear a vote for independent. Okay, tell me why it's independent sampling.
Because you're not replacing them when you take them out.
That makes it dependent, doesn't it?
Oh, what am
Now, that's okay, Tabitha. This is why I want to go over this. Because it's the language from your last project. And your last project asked you whether or not with or without replacement. It is without replacement. It is without replacement because Max is taking the chick and we're going home with it. It's not going back into the bin. He's not playing with it and then putting it back. And they don't like when you do that anyway. That pisses them off actually at the store. So you pick it up, you put it in a box, you get some food, you get some watering things, you go home, you put them in a box, keep the cats away from it, and raise them up with a girlfriend girls. Fair enough so far? So Tabitha says, yes, it is dependent sampling without replacement. I agree. Did anybody say we could treat it as independent sampling? Did anybody think that? Think back to your last project.
Doesn't the project say that you get the same numbers relatively anyway?
Why, Cassie? Thank you. Yes, why?
I don't know why, but I know the percentages are really close.
That's exactly why, friend. Cassie just said. Okay, let's set the stage. Max goes in to grab his first pullet. He reaches into the bin to grab this pullet. What is the chance the one he's about to grab is a girl?
90%.
90% according to the guy at the store, right? Okay, he takes it, puts it in the box, puts it away. Now let's just put a number out there. Let's say there were 1,000 chicks in the store. 1,000 chicks in the store. Fair?
Mm-hmm.
That means there was a 900 out of 1,000 chance that that chick was a girl that he pulled out. Now when he goes back in, what's the chance the next one is a girl? Assuming the first one he got was a girl.
What, like
$8.99
$8.99
out of $9.99,
yeah.
which is arguably what? 90.
Because you're taking one from each side.
You're taking one from a huge group of chickens. So yes, arguably, you can treat this as independent sampling. So those of you that voted independent sampling, you're arguably correct. Those of you that voted dependent sampling, you're definitely correct. Why do we like independent over dependent sampling? Do you remember why? It's okay if you don't. We'll come back to it today. Yes, it's easier to do mathematically. We're about to see that in spades today as we go through this. Fair enough? Good. So here's why I care about this and why I want to instill in you guys why you might want to care about it. What's the chance they're all girls?
90%.
Careful, I bought 4.
Oh, then you're taking some out of the sample, right?
Right, but we're assuming that we're sampling with replacement, mathematically. What do you think?
I'm going to still say 90%.
Okay, 90%, not a problem, not a problem. I walked up to the desk.
Wait,
What, Tabitha, you're still working? I'm sorry.
I can do this.
You can do it. While you're doing it, I'm going to tell you the discussion I had with the gentleman that made his jaw hit the floor. As soon as I walked up there with a little box to pay for. So Max had already picked him up. He's running off to play with the dog that lives there. I put him on the counter, and I had a discussion with him about, like, well, how do you know they're girls and blah, blah. You lift their skirts and check and blah, blah. And that's where the 90% came from. And as soon as he said 90%, I'm like, well, that means there's a 1 in 3 chance I got a rooster in this box. 1 in 3 chance I got a rooster. And he's like, how do you know that? I'm like, well, I'm diseased, first of all. And I think about this all the time. But he gave me all the information I needed to know that. Tabitha, what are you doing right now, my friend? Help me out.
I'm doing 90% of 4, which is 3.6 to the 4th power divided by 4 to the 4th power.
What are you getting?
65%. 60%.
Which is the chance of getting 4 girls out of 4.
Bam.
65%. Remember what I said? I said there's about a 1 in 3 chance there's a rooster in there, which means the other 2/3 is no rooster. 65% is about 2/3, isn't it?
Righteous.
Yeah, righteous indeed. Yours is actually correct to 2 decimal places. Mine is correct to the first 10th place. But nonetheless, yours is more precise. But what blew his mind was he didn't know how I was able to come up with that. And some of you might be sitting there going, how the hell did Tabitha just do that? So what I want to do today is I want to build the flock of my 4 birds from the ground up to show you where the number came from. It is a Project 2 question, but you may not see that right now. You may not see that right now. So what I want to do is, we're going to build this flock. We're going to answer all these questions in time. Okay. We're going to build this flock piece by piece. We're going to start not with 4 birds, not with 4 birds, not with 3 birds. We're going to start with 1 bird. What I want to do, Chestnut, is re-answer your question from before. I want to create a flock. Call it flock number 1. That only has 1 bird in it. Max, go in and grab 1 bird. Go in and grab 1 bird. And come out with that bird. And now I want to analyze that 1 bird flock. What am I interested in, friends? Why am I buying chickens? Why are we buying chickens?
Eggs.
We want eggs, which means we want
Females.
females. So my random variable is going to be defined, this is for me anyway, is number of girls. That's what I care about. It goes back to Chess's question. I could put male and female in this column, couldn't I? I could. But if I quantify it this way as 0 girls or 1 girl, I now have qualitative data listed correctly quantitatively. Does that make sense? Male or female is qualitative, but if I'm talking about the average number of girls, boom, that's quantitative, and it's legitimately quantitative. It's not like calling spilled food into keyboard 1. That's arbitrary. This is correctly quantitatively coding the data, if you will. Fair enough? Makes sense? To re-answer Chess's question before. Awesome. So, I set up the probability distribution on the left-hand side. What would the right-hand side look like? For example, assuming I only bought or maximally picked out 1 bird, what is the chance that we didn't get a girl?
Yeah.
Remember what the guy told me? That I didn't get a girl. 10%. 10%, right? Where's the 90% go? It's got to be here. That's the 90%, because I only bought one bird. Each bird that Max picks up has a 90% chance of being a girl, which means it has a 10% chance of being a boy. And that's represented pretty nicely coded here. 0 girls means 1 boy this is out of 1 bird. So I'll put this here, out of. So 0 girls out of 1 bird has a 10% chance. 1 girl out of 1 bird has a 90% chance. So here's the big picture. The big picture is, what is the average number of girls if I only buy 1 bird? How could you answer that question? What is the average number of girls you would get? It won't be a sensible number, I'll tell you that right now. If I asked you to find the average number of girls based on this distribution, could you do it? If so, how? Could you do it? And if so, how? Well, answer yes to the first one. Yes. Now, how? You could, absolutely. But I think this is such a small distribution, we could probably do it much more quickly manually. Remember how you find the average of a distribution? I know the TI is a great default, and I want to default to it too, Chess, a lot today. Tabitha?
My typical result divided by the sum. So
Yes! But what's the sum of this?
100.
Yes. So we don't even have to do the division because it's already taken care of. Shelby's saying multiply the x's times the p of x's and add them up, which I believe is what you're getting at over there, Tabitha, right? Yeah, Shelby, let's go with it. Yeah. So 0 times 0.1 is 0. 1 times 0.9 is 0.9. So the average number of girls, if we use that, and like I said, I'll happily put this on the board for you guys on Wednesday if you want it. But by all means, just to use your TI. But this is in the background. This is what's going on. This is going to be 0 times 0.1 plus 1 times 0.9, which is 0.9. Which means, on average, per bird, you get 0.9 girls. Does that make sense?
Yeah.
Does that make sense? Not that you get a 0.9 of a girl. It doesn't make any sense. But it's an average. So this means, actually, what does that mean? On average, having 0.9 girls. What does that mean? What does that mean? Compare it to the lollipops we did on one of the first days of class.
Can you repeat the question?
Sure. What does it mean to have an average of 0.9 girls per bird? What does that mean?
So I guess if you have 10 birds, 9 of them will be females.
Yeah. Perfectly said, Raphael. If you've got 10 birds, 9 will be female, which averages to 0.9 over 1. Fair enough? It's like the 1990 census, 2.5 children per family. What the hell does they have a child? On average, it means there's 25 kids per 10 families. But it knocks down to a unit of 1, which averages often do. Remember you guys with lollipops? It would mean if I stood 10 people up here, each holding a bird in their hand. On average, one of them is holding a rooster. So in order to spread the girls evenly, I'd have to take the other 9 and chop off a 1/10 of each and give that 1/10 to this person holding the rooster, who now holds a rooster and 9 little bloody pieces. And the other 9 hold 9/10 of a bloody, bleeding out little... This is disgusting. But that's what it means, minus the bloody and the gore and the disgusting and the SPCA lockdown. But it does mean that. It means an equal share. So, you said it perfectly, Raphael. If you don't like this unit, multiply it out till it's a whole number. Perfect. So, if we just had Bertha, On average, you're going to get 0.9 girls per bird, and there's your distribution. But we didn't just get Bertha. Let's add another bird to the mix. Let's add Nancy. There's Nancy. All right, so now Max has purchased Bertha, the barred rock, and Nancy, the Orpington. By the way, Orpingtons lay very, very well in this climate. I don't know if you guys know. You guys have Orpingtons in your flock? They do pretty well in my flock. I don't know about you guys. All right. So, let's build flock number 2. Flock number 2 over here. Flock number 2. And we got 2 birds. Okay? I still care about the same random variable. I still care how many girls I get. Okay. Number of girls. Because I still want eggs. Oh, you guys have met the girls before. I already made you do a problem on your first exam about it, didn't I? About how many eggs they lay per day from January to April. Did I tell you guys why I only had data through April? Did I tell you that Max shredded the rest of the data? Did I tell you about this?
No.
We make, I love this kid so much. He's so freaking rad. We make bedding out of newspaper. So instead of buying straw, I just shred newspaper and put that in there. It's affordable. It biodegrades beautifully. Chicken poop is amazing fertilizer. I don't know if you guys try to use it for your own gardens. Let it cook for a season to get the nitrates kind of to break down. So newspaper's great. So we're out there, and I kept the data sheets from January through August. And I would just, every day I'd go out, pull the eggs, and write down how many there were in this calendar. And then I was going to collate it and put it on your exam. And I was out there one day, and he likes to make the paper with me. So I got this little shredder out there in newspaper. And I hear him grind. I was out in the main part of the coop filling their water. I heard this, I'm like, oh, Max is making bedding. That's awesome. And I go back in. He's shredded August. He shredded July. He shredded June. And I'm like, oh, dude. And I'm like, oh, the hell with it. I got 4 months. That's fine. So anyway, love that kid. Love him. Okay, number of girls. How many girls can you have?
0, 1, or 2.
0, 1, or 2. You've got 2 birds. There's the combinations of girls you can have. Now realize that 0 girls means they're both boys. 1 girl means the other one's a boy, and 2 girls means there are no boys. Are you starting to see why it's called binomial now? Mm-hmm. Boom. There's the binomiality of it, if you will. Each one of these has a secondary component. You're only defining one of them, but there's another complementary component also back there. Cool? All right. Probability of X. Let's play. What's the chance? Let's just do this one. What's the chance we get any girls at all? What do you think?
Okay, well, if they're all hens equals 65%, then no hens would equal...
Careful. That was when we bought 4 birds, Tabitha. We can't use those numbers yet.
Okay.
We can't. Tabitha's trying to use the 65%. Thank you, by the way. Very, very nice. But we can't use that because that is based off Max buying 4 birds, not 2. Lucas, what do you think? Say that again.
0.2.
Why 0.2?
Well, because you just add over there was 1 bird, and then you're just going to double it.
Okay, I like this idea. So we had, over there it was 0.1.
Yeah.
So if I just double it to 0.2.
Yeah.
Let me ask you a question. Do you think it would be easier or harder to get all roosters if you bought 2 birds or if you bought 1 bird? Would this be easier or harder?
Harder.
It would be harder? It would be harder to get 2 roosters if I bought 2 birds?
I would think it would be
Okay, so I'm getting a little bit of discrepancy here. How many of you say it would be harder to get 2 roosters out of 2 birds than it would be to get 1 rooster out of 1 bird?
It would be harder.
It would be harder. Vote for harder. Some people are saying it would be easier. Now, I'm not saying it's easier to get a rooster. I'm saying it's easier to get both roosters. In other words, he bought 2 birds and they're both roosters. Let me phrase the question again. I'm not saying it's easier to get a rooster. Is it easier or harder to get both roosters? I agree. It's actually easier to get 1 rooster.
Yeah.
But is it harder or easier to have them both be roosters?
Harder.
Okay, now we're in agreement that it's hard. So it has to be less than 10%, doesn't it?
So we would take the 10% and times itself.
Now, wait a minute now. I heard before 0.1 times 2, which would be 20%, which actually would be easier to get 2. Now I'm hearing 0.1 times 0.1 multiplied by. So the difference is, do we add them or do we multiply them? I'm here to vote for multiplying, but they didn't say multiply. Who wants to back her up on this one?
I would say that.
We got a second, we got a third, we got a fourth. All in favor of multiplication of the 0.1 of the 0.1? All opposed? Discussion? Hell yeah, discussion.
You're not sure.
Why? You're 100% correct, Athena. Why are you 100% correct?
Because
Let's talk it out. Let's talk it out using the language from Project 2. In order to have no girls, we have to have what?
Boys.
Both boys, right? That means that Bertha has to be a boy.
And.
Say it loudly.
And.
And Nancy has to be a boy. And what does and mean? Multiply. Think to your second project. What does or mean? Or means to add. We're going to see some adding in here too. But right now, for this, if we want no girls, we have to have both boys. Which means Bertha has to be a boy and Nancy has to be a boy. For sure. Which is 1 in 100. Which hopefully makes sense. That's now 10 times harder to get 2 Brewsters as it is to get 1. That should make sense. It's 1/10 likely each time. So each time it gets harder and it's exponential decay. It's exponential decay. It's exponentially harder each time you pick up a bird. Because that bird has to be the 1 in 10 that's a boy. Fair enough? Decent?
Yeah.
Let's apply that same logic down here. Okay? Let's skip this one for a second and come down to here. What's the chance of getting 2 girls? Use the same logic.
So 0.9 times 0.9.
It has to be, doesn't it?
Yeah.
Because in order to get 2 girls, Bertha has to be a girl, 0.9, and Nancy has to be a girl. So this is 0.81. Fair enough? Yeah?
Yeah.
Ish? Fair? Good. So knowing this, practice for Wednesday. What is the probability of only getting 1?
0.18%.
Girl.
Well, point,
We have a vote for 0.18. Tabitha, go ahead. What are you saying? What are you saying? Walk me through the process. Go for it.
Yeah.
well, 81 plus 1.
Is 82. The remainder is 18%. So we know the remainder. I'm going to put it out here for a second. I'm going to put it out here for just a second. It seems kind of stupid to put it out there, but I think I know where we're going with this. How could we calculate that? How could we, like we did here, could we calculate it like this? Sure. So say that again. Athena, say that out loud. Say that out loud. What did you just say?
I don't know what I said.
You just said 0.1 times. Yes! So if you go 0.1 times 0.9, that's a boy and a girl, isn't it? A boy and a girl. The problem with this is that's only 9%. And it needs to equal 18.
But it could be either way.
That's the difference. If you put 0.1 and 0.9, this means Bertha's the boy and Nancy's the girl.
What if Nancy's the girl, Bertha's the boy?
What if, or Bertha's the girl and Nancy's the boy, and that's exactly correct. You have to,
Add both possibilities.
yes, and why do you have to add? Say it out loud. Say it with me. In order for, make sure you guys can see this. In order for, out of these 2 birds, exactly one to be a girl, either Bertha's a boy and Nancy's a girl, or Bertha's a,
Boy.
well, I think we did that already. So Bertha's the girl and Nancy's the boy. Did I say it wrong the first time?
I don't know.
Let me say it again. Either Bertha's the boy and Nancy's the girl, or Bertha's the girl and Nancy's the boy. You hear how the word or was in there and a couple of word ands? And they're all there. They're all there. The ands mean multiply and the ors mean to add. So it's both projects coming together in one place now. Pretty rad, huh? I think it's pretty rad. You're just tired because it's week 7. That's okay. It's understandable. Fair enough? Now, that is a little bit annoying mathematically, isn't it?
It makes sense though.
It does make sense. I totally agree with you, Cassie. However, there is a bit of a shortcut once you understand the different ways to kind of spread that out. Mathematically, this is 9% and so is that. So what we often do, rather than doing that, we simply keep track of all those outcomes out here and put a 2 out there. So double, because there are 2 ways for it to happen. So that would have been the 18 over here and kind of put it in line. Is that fair? Believable? Believable? So then the trick is just knowing how to calculate that number. We're getting to that. Yes, we're doing fine. We'll do it by the end. The question is, how do we actually figure out what that coefficient is? It's called the binomial coefficient. Very, very, very pretty number. So, okay, you ready? Very often, the most important number that we want from this is, how about the average? What's the average number of girls per 2 birds? Raphael could already answer this without even doing any mathematics, I guarantee him. No pressure, brother, no pressure, no pressure. But if I asked you to find the average, how would you do it? How could you do it?
Well,
If I asked you to find the average of that distribution, what could you do? You could run your one bar stats, could you not? Tabitha, what are you looking at?
The equation.
Yes, you are. She looked, I wasn't like a threat. What are you looking at? No, she was looking at the correct thing. She was looking at the average of a distribution. So you could do 0 times 0.01, which is 0. 1 times 0.18, which is 0.18. And 2 times 0.1, which is 1.62. 1.62 plus, it should be 1.8. 1.8 girls per 2 birds. How did it go?
I don't know what I did, because
What
I'm
did you
still
do?
back in the joint probability where we did
Yes, ma'am.
event face over sample.
Yes,
space.
ma'am.
So I just took 2 and multiplied it times 90%, I got 1.8.
Wouldn't that give you the exact same thing all the time up here?